Welcome everyone to today's live stream, Programming 101, today RISC-V. This is not yet a fully structured episode, this is basically a test, as many people always ask about Programming 101 and more programming. If you're a subscriber to this channel, you know that we are a little bit annoyed by the complexity and bugs of software and hardware and always envision smaller, more minimal solutions and not only microkernel stuff. And so I wanted to explore what does it even take. I said so often like 10% of the size or 90% smaller. And certainly fan of, actually should have prepared better and RISC-V and stuff, right? The new instruction set. And so let's take a closer look. We had the previous video with RISC-V instructions. And so the last days I took a closer look. What does it take if we create new, not only, well, also eventually an operating system, but like a whole tool chain, for example. Of course, there are the good old GNU tools written in C and quite large in size that everyone, including our Linux distribution, is using. GNU binutils and otherwise LLVM Clang, of course, but both projects are huge. And the question is, what does it even take to get started after apocalypse or just for science? And so this is a RISC-V RV32i base instruction set. And to my surprise, I usually was quite a fan of RISC-V. Let me just, right, this is also search, can we get rid? So, even I was surprised that the base instruction set fits on one page. So this is, let me just check if that is mostly in time and welcome. Everyone, Dr. Schubert asks for the use of the microkernel. Yes, for example, more to that in a second, but you get to start somewhere. And this is also the fun stuff, right, that I want to do more, like more research. Although, yeah, assembler is not rocket science research, but hey, just-in-time compilation, right? There are not yet so many just-in-time compiler, for example, for RISC-V, and so on, and also programming language, right? I criticize usually C, C++, and Rust is amazing, but a little bit huge. So yeah, this is a base instruction set, and this fits on one page, right? So this ends here, and this is, it's not continuing there. This is RV64 base instruction set. So it continues with other like RV64, 64-bit, and other extensions. So the whole freaking instruction set that is not as complex as x86, which fits on hundreds of pages with all the crazy encoding and so on. So we have in RISC-V, how does it work? And again, so this is a quick test, right? I want to see how many views does it get, how many people are interested and stuff. So you probably want to share, like, and subscribe and so on. And you probably want to watch the previous video on the more main channel, RISC-V instruction set architecture. So after watching that video, so we have in RISC-V, the instruction set is rather reduced, and the various instructions like adding numbers, multiplying numbers, jumping, comparing, and so on are made out of those types here: R, I, S, B, U, and J. And the difference is the use of those bits. So they're all 32-bit, except if you also have the compressed extension that is 16-bit, but doesn't matter too much. Otherwise, let's focus on the base. These are compressed extensions anyway. So the non-compressed, the base instruction set are those types. And we need those because instructions, whether it's an addition or a jump and so on, they need different fields. So this is why there are these different types. As you see here, for example, here is, I think, load, whatever U was, immediate, maybe unsigned, immediate, whatever. But as you see here, so this is here the immediate U type of the opcode, the destination register, and then how many bits this are, like 11 bits or so. 11, doesn't matter. From 12 to, so this is, doesn't matter. Let's not try calculating here, then we have computers for that. So, and as you see, all the other instructions need more, like obviously if you load an immediate value, then you only need a destination register. If you do stuff like logic operations here, XOR and stuff, so they all share the same base opcode here in binary 0010011, and they differentiate here's a different, whether it's an add. It's, by the way, it's not the best example as this is add with immediate, but the difference of these instructions is encoded here with the additional function 3 bits and in others additional function 7 bits. So for example, here with the real logic operations, where I just looked into the wrong line, the more regular ones without immediate, they use this encoding here, that is that R, I guess, and they all share the same logic operation opcode here, 001, 0011, and then the different kind of operation here, as well as in some cases, for example, shift and others, add and subtract, for example, are the same, and the sign of that is encoded in those bits. Of course, many of those bits are 0 for other variants, for future extensions, and so on. There's also atomic and 64-bit, and so on and so on. But this is the basic coding, and this is what I also appreciate and like with RISC-V, the fresh start of something truly reduced and regular and so on. So given that this is, and this is also my point of, I want simpler stuff, and continuing this year on, unfortunately not invented here, rewriting from scratch because too much C and too big. So what I envision is an assembler that doesn't fit on one page of paper, but at least like, is it possible to write a whole assembler, let's say in like 10,000 lines of code, and maybe not support all exotic features and stuff, but trying it as simple as possible. So that's what I started to draft. So this is not a full assembler, this is just a dozen of lines what you do after work that I started to test already. So how does an assembler work? So this is basically the episode -1. Let's try some presentation style and see if people are interested and how we can fast forward with that. So what does an assembler do? So assembler, we need an assembler for our just-in-time compiler, and for example, either supporting Rust or some variant of that, or JITting, just-in-time compiling JavaScript or Lua, or whatever variant we want to do. So assembler looks like this. Here on the screen, it's just some examples. This is generated by GCC, but it doesn't matter at all. You could also theoretically write this from scratch by hand, for example. So this is how I think this was. What did I write here? This was, I think this. Do I still have that around? Maybe I think this I compiled simply Hello World. This might be a whole Hello World application actually. I think I used cross-compile do chain and compiled here, or yeah, Hello World example. So this is Hello World. So this is basically a whole application printing Hello World. But that doesn't matter too much. So this is how on what a CPU operates on. Whether it's RISC-V or PowerPC is similar, even x86 is similar, just vastly more complex. So a CPU looks on those in-memory encodings that we can also like use bin utils to bootstrap, so object dump, this disassembly, and so this is the in-memory representation of those numbers. And the CPU with each instruction cycle reads this memory at the current instruction pointer, CPU register, program counter, and then internally the logic of the CPU, RISC-V CPU or your AMD EPIC Threadripping Ryzen needs for each of those instructions, and for x86 it's way significantly more complex, obviously with variable length encoding. I have a previous video to that too. But for RISC-V it's super simple. So what the CPU needs to do is simply match here those bits, of course implemented in silicon and logic gates, and so it's matching those bits, and of course it doesn't need to compare all those bits, it only needs to compare and branch in logic, similar what we have done ourselves previously in FPGA episodes. Compare those bits here. And so, for example, at this immediate would be Z here, so that should, I didn't check that, but I trust binutil that it probably disassembled that correctly. So that would be 0, 0, 1, 0, 0, 1, 1. Add with immediate, here stack pointer minus 16, and that minus 16 is encoded here in this immediate bits with the source and destination. So this is adding the stack pointer, so this is encoding. So this is how a quick, very brief, quick look how CPUs work internally. And what we need to do to write a whole tool chain, whether it's a static assembler for good old-fashioned languages or like JavaScript doing this in a web browser dynamically on the fly just in time, we need to create those bit patterns, right? So an assembler is actually super simple, which is also why I don't really want 100,000 of lines of code in binutils. And spoiler alert, I today looked into binutils, the RISC-V backend. It's like, yeah, the readability leaves a little bit, leaves a little bit to be desired. So this should be relatively simple, right? So I've not written this in one day or one afternoon, but I took a closer look, and yes, spoiler alert, I drafted this in Lua because why would you write this in C like binutils? And I also tested around here with, so this is just a dozen lines of code to see how much code do we really need. So what we basically need to do is we need to copy and paste those bit patterns here out of the standard specification. I tried to find a source, I didn't really find a better source, so I actually really copy and pasted it. So this, even in Apple's preview, usually I use Linux, but live streaming from my M1 Mac, so Apple preview is not the worst, but even that, like selecting this, good luck. Also, yeah, Apple's preview is actually one of the better ones, but I had to post-process this a little bit here with some SED and stuff, and pasted that together. I saved this here, so this is like pasting those with your PDF applications. I wish there would be a machine readable format. I didn't find any in like 15 minutes of Googling. Like, yeah, recurring theme, you Google for some stuff, and in the end you copy and paste it and SED the stuff together. Because what we need is a table of these instructions. So the assembler needs to pass the source, obviously the human input. I also, let's, for example here. And so either what the human has written, because it's the Linux kernel early startup code, or it's the output of GCC or LLVM Clang, and we need to assemble this, right? In a future episode, we will obviously write either a minimal C implementation or other languages. But for today, let's focus on the assembler. So we somehow need to transform this stuff into this bit pattern, right? Because that is the machine code that CPUs operate on. So we need to build a table, and obviously with RISC CPUs, that is way easier than the variable complex craziness that is x86. And so for that, we need to create this table. I started to do that, and thankfully this are not too many. And then for each line of code that we pass here, and obviously in Lua that is way more convenient than in C with pointers and out-of-bound conditions. That's why I still wonder why people still write this stuff in C. So parsing this is, if you are not doing this in C, this is super simple, right? Splitting the stuff on spaces and commas. Actually, this is not the assembly. The assembly, of course, has commas. So the original assembly looks like this. This is already parsed. So depending on your input format, whether this is AT&T or Intel variant or any other kind of vendor assembly syntax, you simply parse this line by line. This is, of course, Programmers 101 in your basic book or first lesson in school or so. Separating this strings, splitting those at spaces, at commas. This is not a big deal, right? If you do this in Lua, you can do this in one or two lines of matching strings. Separating this instruction, so the instructions would be those as the registers, and then simply looking this like each instruction, looking this up in your table, right? Obviously way more convenient in Lua than in C, where you don't have any associative arrays, hash tables and stuff. Obviously a little bit more convenient in C++. And then generating those bit patterns, right? Bit patterns meaning we need to also look up the registers and of course issue diagnostics if you specify your registers that don't exist, like typing instead of X1, Y1 or A1 and stuff. And outputting diagnostics of, hey, human, the stuff doesn't exist. And after we validated the stuff a little bit, that makes somewhat sense and doesn't fit into this format, then encode this bit patterns, right? This bit patterns here for the instruction, for cases are branches. Here's also load bytes, so this would be immediate bytes here, other logic operations, and simply encoding this, right? And I've not finished this in one afternoon. We passed this already, so this is also where I want, obviously the new stuff I don't write in C at all. I said this before, we would at least use lightweight C++ to gain, to remain somewhat sane. I'm not yet sure. Rust is, the stuff is statically typed languages often get rather out of hands in lines of code. Often you end up writing dozens of lines of code of statically typing stuff, and so I'm not yet 100% set on what kind of language I want to build the system. This is why prototyping this in Lua, actually you can relatively, well, first you can get the stuff working and then you can still transfer this in some other language. So parsing this, splitting this line by line, right, for lines, this is an in-memory string buffer, otherwise you could just use IO lines, but we are parsing here some in-memory string. So this string we get matching this for new lines, removing comments, of course. So this would be the steps, right? Programming 101, machine parsing some language. For example, comments, sure, I'm aware there are plenty of parser generators, but we want to keep the stuff as minimal and bootstrapping as possible. So open, without a parser generator, coding this from scratch, breaking at new lines, removing comments, splitting that on spaces or commas. So this is comma or spaces. And I fill this here simply in one I for instruction table in Lua, some basically a fancy variable length array and hash capabilities, associative array capabilities. And then we look up this instruction. Right now I use it to upper. Ideally I would, that doesn't matter too much. This is just totally irrelevant. I'm looking this up in our instruction table that we extracted from the PDF. This is basically this here. This is not complete. We would need a little bit more description. I only wanted to see how far can I get after work in like 2 hours. And then to our surprise, not all those instructions exist because there are also some pseudo extra instructions. So of course I knew this. This is writing this stuff from scratch. So it turns out some of those instructions are not even real instructions. For example, here move, mv, move, or I think li, as well as ret. Those instructions actually do not exist. What they have done here is, and they often do in other architectures as well, they define some pseudo instructions, because turns out often as a human you want to write something easy and understandable like mv for move, but internally they didn't want to waste in RISC-V opcode for move, but they just reuse other stuff, because turns out move, which exists in other instructions that, as a dedicated instruction. In many RISC architectures, you simply, also in MIPS, for example, you just reuse other instructions. For example, here, add with immediate. Here, for example, add I destination source 0. So this is basically moving from another source register, adding 0, basically. Yeah, this is just an alternative encoding. Of course, you could theoretically do this with other operations as well, for example, or subtract and stuff. But what instruction set architects often do is reserving one encoding. So for example, that assemblers and disassemblers all agree on the same. It architecturally doesn't even matter too much, except that Silicon implementing the RISC-V instruction set could use such a special like add immediate with 0 as a special form of move internally for the microarchitecture to potentially optimize some details. Similar knob doesn't exist, so knob is simply adding the same add with immediate to the 0 register, which anyway is always 0, right? So this is adding to the always 0 register, which is always 0, 0. It's like, yeah, the whole stuff obviously doesn't do anything, which is no operation. And similar to our return, also, yeah, li load immediate, for example, because the RISC-V instruction set is 32-bit fixed, unless you have 64-bit or 16-bit compressed instructions, but otherwise it's regularly 32-bit. You can't load 32-bit obviously, because there are already some bits for the opcode like 0, 110 something. So there is a maximum of whatever we scroll this away, I think like 12 or so, 12 or 13 bits that you can load with. Actually, we have this here. So load immediate a whole 32-bit. Whole 32-bit is actually a multiple instruction sequence for RISC-V. So that would be this one here: load byte, half word, double word, destination register, and so load here some global. I think so, at least I think it should be that one. So that is. So I'm not entirely sure if it's this one. Maybe it's not. Where's the immediate? Actually, I'm not entirely. Maybe it's not that one, actually. Because this is, or is it that? Anyway, I would need to look up what AUIPC is. But so you have here the 32 bits 12 to 31. And then loading here additionally the LBH, what is it here? Anyway, so basically this is composed out of 2 instructions of loading the high bits as well as adding the low 12 bits. And actually I think these are 20. Does it make this 20 bits? No, it doesn't, because these are 12 bits. So, and return similar is, return is jump link register, I think, at least as far as I remember. And with XO here, return from subroutine. And we need to encode those, so I started. So that is the major complication here in our assembler testbed. I started to encode this, so we would need to make some kind of special support for translating pseudo instructions to a sequence of other instructions. We could do this in multiple ways. We could either add here functions to generate those, as we are already right now drafting in Lua. We could use as a scripting glue language of on-the-fly generating this. We could use similar to GCC or other invented some template language. For example, here that we use some kind of escape sequences. By the way, I think I left here an ADD, forgotten. So for example, using move, so that we have here some arguments, for example, move onto 2. So there are multiple ways. Then here also we would, the only thing is we would here for data immediate arguments, we would need to have some kind of bits annotation here, so that our assembler needs to know what kind of bits it masks off of there. But this could also work similar. For example, we would of course need to have some string escape format handling. Then for this pseudo instructions here, this would be then the immediate. So if we support something like that, then that would be something like that. Maybe need to think. So basically, this would be like whatever is easiest to implement. This is just some idea, and that is the major complication. Plus, there is one more thing, which is the register names. So RISC-V is usually using register names simply X for the registers X to 31 and F, X for integer and F for floating point registers. And they also have here human readable ABI names. X0 is 0 because it's always 0, and then otherwise we have RA for return address, SP stack pointer, as well as temporary and saved registers and function arguments, so that it's easier. Well, for the compiler it doesn't matter at all, but making it easier for humans to read this, so they don't need to constantly remember that X10 to 11 were the function argument and return values. And that is of course also not a major thing. We would simply create a similar lookup table for the register names, so that we simply internally translate those ABI names like any register argument, looking this up from ABI names to internal register names. That is of course totally not a big deal. So with that, of course in the end, so with just some 2 hours of after work time, you of course don't have a full assembler, but something that starts to parse the stuff, starts to look it up. For the instructions, we would need to have a little bit more complex structure, because as you have seen, right now I've only encoded the base opcode, and we also need the other function 3 and function, like additional 3 and 7 bits here for the opcode. Other implementation details would be whether we want to internally like group those. For example, we could use this knowledge. This would be a little bit of... initially I thought I simply dump those into a table, which would be the most mechanical and automatable way to do that. I looked into the bin utils, the GNU bin utils, and the code is a little bit, it's C, so, and I only saw, I think, from the 5 minutes I looked into that bin util there, it looked to me that they used the knowledge of having load, like they have like load logic and stuff. So we could do the same. I'm not entirely sure how valuable it is. I'm somewhat still inclined not to do that. So basically simply dumping this instruction table as it is there and not manually regrouping stuff, because it's manual labor, time consuming and error prone. But leave in the comments below what you would do. I will see. My goal would be to, within weeks, have a functional assembler. The only other thing we would need to do, so I think like in just some days, like with some intermediate knowledge of programming, within some days, you could have a working assembler. Not too much. And disassembler, right? So disassembler is the same, right? Like what a disassembler is, if you have a binary, like here you compile this and you want to actually review that here. So object dump -d -j for the section by default. Somehow object dump stupidly disassembles all section, even if they contain data. It's a little bit silly to me, but yeah, that's what it is. And disassembler works just the same way, right? Similar to a CPU, no magic here. You have those binary machine code representations, and similar to the CPU for each instruction cycle, you simply look up this bit pattern and print out, like basically obviously the reverse process of an assembler, but not. I mean, somewhat it's even easier because you do not have any text parsing to do, and you simply can look up those bits and print them out. So I would say disassembler is even simpler. The only thing is the GNU disassembler already decodes those pseudo instructions elegantly. That is certainly some value added feature of not printing at immediate A0, A5, 0. So they actually in the GNU object dump binary format library recognize those pseudo instructions and print them out nicer for you human reading pleasure here, as well as they obviously print the ABI names here as you see, so they don't print X 01 and so on. They print here SP for the stack pointer, RA as you can see here, and A0 for example. And yeah, the only other additional thing would be that we need to, well, depending on the object format, so that is basically everything you would need for an assembler and disassembler, and well, except wiring all the stuff up and make it work, obviously, the nitty-gritty details of some days of implementing and debugging and guru meditation. The only other thing is dealing with these object formats. As you see here, read elf-a hello object. Usually we do not work with raw binary files. You can do that. I've also done that. Previous video was running GCC executables on DOS. This dumping this raw for COM executables. But on Unix and other systems, we usually have some surrounding object formats, so we would need to spend a couple of additional hours, more likely a couple of days, implementing all of those. What this does is we need some surrounding information, right? If you dump this machine code numbers just in a file, you have no context, and you need some context. For example, that is what the ELF format, for example, previous AOut or otherwise on Windows PE format. What this encodes is here, for example, starting with the magic of this is an ELF file, and including stuff like the machine type, RISC-V. For example, this is stuff we would need to know. We would need to know this is ELF 32-bit. This is RISC-V. The other surrounding stuff is like, yeah, we don't really need that. But what we need is all those sections, because in a real program we have more than this machine code. We have some surrounding data and symbol tables. And data is magic numbers, like you write some algorithms that include some like JPEG compression or stuff, previous video. You have some magic numbers for file offsets, for magic numbers for the file magic, for string comparison and so on. So you have tons of magic numbers of string data, like say you print hello world, you have hello world is your magic text string, and all of those you have in your data section. And here's some other surrounding sections, zero initialized data and stuff, but also symbols. And in this example, for example, we have some symbols that we don't need for the final program. For example, that this was here some file node here of type file here of hello C that we compiled this from. We also have some symbol names for the section names. For example, this is how the ELF format works internally. But we also have here put S, and like we have a function name. So this is here, all those symbols are referenced by index here in this ELF format. So we have actually, well, we have all the section names that we need to decode the ELF format, and we have the main symbol here, function type main. We obviously need that for linking that. So next we would also need to write a linker, obviously. Linker is relatively simple, just dealing with combining multiple of those, simple and simple, but mostly simpler, certainly simpler than a programming language and simpler than this assembler. Combining multiple files and relocating, or finally relocating, aka resolving all the jump and call addresses here. And for example here, we also need a C library. In this case, we reference a C library, and this is where this global undefined put S is coming from. I actually think we don't have we don't write putf. I think this is an optimization of, okay, let's do it like that. Source T2. I'm pretty sure this example most likely used printf. Let's archive, hello. Yeah, printf. So that looks to be an optimization from gcc/glibc to optimize, apparently, as far as I can tell here, printf without any format to putf, apparently. So there are some additional complexities surrounding that, dealing with the object format and actually linking this stuff together at the end. But that is a 35-minute presentation of what it takes to parse, assemble, well, at least the basics. As you can see, leave in the comments below if you found this helpful, what kind of details you want to see. So basically, as I said in the beginning, this is a test, a quick and dirty Friday evening stream. And welcome everyone. So this basically tests how many people we get. This is also why obviously we had a lot of stuff to do with our T2 Linux, actually getting all the stuff to work and fix and implement features. Certainly a little bit busy. And also I'm not entirely sure how many views we get. Certainly doesn't make the most sense if the problem, obviously, as you can see, this presentation I can do after work if I create a university style presentations and I need a couple of days to create presentation slides. So basically this is a test. Leave in the comments below if you found this helpful and learned something, if you want to see more of this stuff. For me personally, of course, I knew all those details from university and dealing with the GNU toolchain and now LLVM Clang the last decades, especially with in the context of our Linux distribution. It is mostly that certainly the GNU toolchain stuff and LLVM Clang are fully featured, except that they do not support the vector extensions yet, let alone the bit manipulation extension. Also, of course, there are patches for that. But I'm mostly dissatisfied of having everything in C on the GNU side and everything in the LLVM Clang side. LLVM Clang somewhat more amazing, but unfortunately also huge, right? So I'm somewhat tempted to create a truly minimal system, as I said already 100 times on this channel, of 90% of the features with maybe 10% of the code or so. Certainly, you probably want to share, like, and subscribe to see how that is going. Let's take a quick look to the comments. Welcome everyone. Santa Pay 11 or so. Sorry for name pronunciation. Ask MIT white papers Berkeley. I'm not really sure what you mean. So this was the official RISC-V org. This is not white papers. If you mean these are the official instruction. This is RISC-V spec 2019-12-13. So these are the official ISA downloads from the RISC-V org website, if you mean those. Dr. Schubert says pseudo instructions also on IA64, compare NE, compare equal with destination predicate register swapped. Greetings to Darmstadt. And want to see, okay, so some people want to see more of this. This is amazing. I intentionally keep this short, right? So we have some comments, which is amazing, but as I learned, if we continue on like some question and answer for some 30 minutes, then the video is, instead of 40 minutes, 60 minutes, and then less people watch it. So was amazing to see you all. It's just that for YouTube and the algorithm and people watching it, we need to keep it somewhat brief. So if you have further comments, leave them below, and I hope a lot of people share, like, and subscribe it so that we can try to bring this kind of format to a ongoing series of programming 101, how CPUs or how computers work, how memory works, how CPUs work, assembler, linker, higher level languages, and so on. Everything that belongs to Z. And I hope to see you all for all the next videos and live streams to come.